is about calorimetry at the Electron-Ion collider. Where is yours?
All right, good morning. Nice to see everybody again, though I'm bad with faces, so if someone's here who wasn't here yesterday or is missing, I would not notice. Yesterday, we talked about polarimetry, and calorimetry doesn't have a whole lot in common, but I am nothing if not adventurous, so I'm going to pretend they do. Yesterday, I introduced the interest in understanding the origin of the proton spin. How is it carried by its constituents? And I showed you some of the history of that. I talked about the different ways we could measure it. I motivated all the stuff we could do at the EIC. And then I showed you longitudinal asymmetries. And again, the math really connects the measurements we can make to these partonic spin pure versions. And all I've done here is just change the bottom 2 points on the slide. In DIS or in CITUS, we can discriminate between the different possible configurations, but we have to identify the electron momentum vector and for CITUS, other final state vectors. So how do we do that? Well, we have to combine different detectors, the EM-cal, the H-cal, the tracking, to measure the particle properties and identify them so we can put together either our precise electron final state or our precise electron final state and something about the rest of the state that makes it semi-inclusive. All right, so there's our DIS. Now what? Well, we're going to have to measure that electron. It's not that hard. We need the opening angle with respect to the beamline, and we need the electron final state energy. We'll call the master control room and ask them what the initial state energy was. And then we can fill out all we need to completely determine the system. So we'll just put something there. It's a calorimeter, and it's going to measure the energy. And I'm going to segment it so that from which one my electron strikes, I get the angle. And in principle, I can just run this as my experiment. This is a dramatic oversimplification. Do not try to build your detector this way. What is a calorimeter? Classically, it's a device to measure the heat generated in a process. Here is Lavoisier and Laplace, and this is a plate in some book from the 1800s. They had a trick. Measure how much ice melts, and you know how much heat was transferred to the X. So if you have kind of slushy ice, and you watch its level go down, you know the volume of ice that turned into water, and that is directly proportional to the amount of energy you dumped into it. So in principle, we could do that. I can make these out of ice blocks, keep them right at the threshold of melting, then just measure the water that drips off, which block it comes off of. And now I can do my DIS. Yeah, obviously, we don't want to do it that way. In modern physics calorimetry, a calorimeter will measure the energy of the particle, and we're going to do that through those EM interactions, same thing, but then convert the energy to an electronic signal rather than liquid water. And generally that we do that by producing an amount of light and then converting that light into a voltage. It's not my job to tell you all about all the detectors that go into it, so this is just a really fast review. Have you had a detector talk already or not yet?
No.
Oh, man.
Go ahead.
Go ahead, please.
Okay. So the task of the detector is to measure kind of four vectors: the energy and momentum vector, the time and position vector, and then through other methods, maybe the identity of the particle that was at those places at those times with those momenta. This is kind of upside down. So imagine your beamline is up here. We have a hard collision up here somewhere, and it sends various kinds of particles down through our detector. This is the canonical way to assemble it. You have some very precise tracking to figure out exactly where these particles came from and when. Then we have some large tracking in a volume of the magnetic field to figure out their momentum vector. And then we might have some other stuff, PID, to measure the velocity or something else that allows us to get a good, clean idea of what particle it was. Then there are calorimeters. Depending on what particle, they will either deposit their energy here or pass on through. So I've got my photon here. It's neutral, so it goes straight through everything until it interacts with the electromagnetic calorimeter. If we didn't have that, we wouldn't be able to see that the photon was there at all. We couldn't reconstruct the entire collision. So the EM calorimeter measures charged and neutral particles that interact through electromagnetism. And then, we got to put the magnet for our tracking device somewhere. Generally, it goes outside of that. Then the hadronic calorimeter has more space. It can be big. Measures roughly the position and energy deposited by charged and neutral particles that interact through nuclear or electromagnetic processes if they make it that far. And all these things, I think it's the energy deposited. We'd like it to be, hey, what is the energy of the particle? But if it continues on through, like this charged hadron, we'll see some energy signal in the electromagnetic calorimeter, but we're not going to get the total energy of that particle until we absorb it. And then finally, we'll put a muon detector at the end. And it's basically just to look for things that didn't stop yet. And the things that we know that don't stop yet are the muons. Okay, now we get to the outline. Intro is done. Next, I'm going to talk to you about electromagnetic calorimetry. Talk about the physics of an electromagnetic shower, how we design a calorimeter, how they perform, and then I'll kind of do the same thing for hadronic calorimetry and kind of wrap up by trying to connect it into EPIC and other future stuff. Okay. The first thing I want to know about is photons. Photons, when they interact with matter, there's a variety of things they can do as a function of the energy. So here we have the photon energy from 10 eV to 100 GeV, and then the cross section for various processes, and I put them in this fun little table. Above 100 MeV, the dominant one is this kappa nuke, which is pair production. And then underneath it at high energy is kappa E, which is triplet production. Do folks know what pair production and triplet production are in this context? Who says, who does? Yeah.
Can you explain that one?
Well, look, do you know what pair production is?
Yeah.
What is pair production?
Oh, to convert the gamma into electron and position pair.
Yeah. So a gamma has no mass, which means it cannot spontaneously decay into an E plus E minus. But in the strong fields near a nucleus, it can do that. Basically, it's scattering off a virtual photon and producing an E plus E minus final state. Triplet production is the same thing, but instead of in a nucleus, it's doing it off of an atomic electron. And so we didn't actually make an extra electron. We just knocked it out of the atomic orbitals. So the net here is that we have 3 energetic leptons flowing forward. And so that's called triplet production. And up above 100 MeV, those dominate, and they're more or less flat. And then below that, we have the cross-section rising dramatically through giant dipole. That one's kind of an oddball. But Compton scattering, Rayleigh scattering, and the photoelectric effect, they all have different Z dependencies. The related question is, how far does a photon go before it undergoes one of these processes? And for reasons that'll become apparent later, we define its mean free path, lambda, as 9/7 of this other thing, x naught. And it's got a complicated structure, but this z over z plus 1 over this logarithmic rise log something over root z. So what does that look like? A high energy photon comes from our interaction over a GeV. It hits our lead block. What happens? Serious question. Just said it on the previous slide. Pair production. Bam. All right. So a little detail. It's neutral. So it's not going to do something just when it shows up. It's going to travel some distance in. On average in lead, the 9/7 of x naught is about 0.7 centimeters. So it'll go 7 millimeters in, and then it will probably pair produce. Bam. That absorbs the electron, the photon. It's gone. Now we have electron and a positron that are continuing on. Each of them carries on average about half the energy of the incident photon. So next question, what do the electron and the positron do inside the shower? It's not quite the same plot as before. This is no longer the cross section. This is the fractional energy loss per radiation length. So X naught, I haven't named it yet. That's the radiation length. And that is defined for the electron or the positron. It's how far they go to lose 1 e-fold of their energy. So over 1 radiation length, they go from their energy to 65% of their energy. But the same arguments that I made before are going to hold here. Above around 100 MeV, one process dominates. That's bremsstrahlung, where an electron emits in the presence of an external magnetic field, it emits energetic photon. But that's a little bit of an oversimplification. It doesn't emit a single photon. It emits a spectrum where the power per unit energy of the photon is about flat. So you get a bunch of really soft photons on one end and very, very few, very, very hard photons on the other end. But the upshot of this is that generally there'll be one highest energy photon that's emitted, and that's the one we're going to care most about. As we go down in energy, ionization starts to take over, and it's a little bit different for electrons and positrons. And that's because electrons can undergo molar scattering and positrons can undergo Babel scattering, and the cross sections are just a little bit different. And then it's different again because positrons, when they get really slow, they can annihilate off of electrons in the material. So you get a little bit of extra energy by stealing half an MeV of energy from the material itself. All right, back to our cartoon. So we had our photon. It strikes this ball. Slides out of order or is missing. But yeah, there's our bremsstrahlung. They both emit one most energetic photon, which I meant to delete from that so I could ask you that question. Let's see. We have 1 GeV to start, split evenly between the two. That gives us half a GeV each. And then they're going to emit approximately 36%. That's 1 e-fold of their energy divided. Two-thirds goes into them, 1/3 goes into the most energetic photon. And that's going to happen twice. So we had 1 particle. Now we have 2 particles. And now we have 4 particles. Thankfully, I've already done the math for this. I know what each of these things does. So then what? Yeah, again, this photon is going to do the same thing that that one did, only a smaller energy. Same for that one and that one and that one. And then what? Again, and again, and again. And eventually this process is going to drop below that 100 MeV level. The cross-section is going to stop being dominated by these processes that add extra particles to the system, and they'll start to be competing with processes that take particles out of the system. So this is not going to grow forever. Eventually the mean number or the mean energy per particle in this effect is going to drop below the critical energy. And now, although some of them might still be producing extras, on average, they're going away. And of course, along the whole way, they're depositing energy. So just because this is dominated by that one most energetic bremsstrahlung photon doesn't mean it's not shedding soft photons into the system that are well below this critical energy the whole time. So as soon as we start scattering, we're going to start depositing energy in the calorimeter that we can observe. So I just flipped it on its side because this plot is showing us the profile as we go deeper and deeper into our material. And as a function of energy, the energy deposited per centimeter, it peaks early, then later and later and later as we go. And that's moving what's called the shower maximum. I think this slide's also out of order. Yeah, so above this critical energy, we are still producing, and when we are when the energy on average, the initial energy divided by our critical energy tells us how many e-folds in we get. And the same just as before, it gets absorbed eventually. All right, so let's review. This is not quite the same system. I'm going to start now with the positron. when it hits our block, what happens? Strong first. Great. But now there's also another difference. The photon traveled into the material a little bit, some fraction of this radiation length before we got enough, before we randomly rolled the dice and got that hard pair production. This one is going to start emitting photons right away. So it's going to emit by chance this sufficiently energetic photon earlier than the first branching happens for the photon starting state on average. And then the process continues from there. We get the same sort of thing. But we can actually see from the longitudinal shower state, that is the energy deposition as a function of depth into the detector, that we can tell a little bit the difference between photons, which is in blue, and electrons, which are in red. This is the fraction of the shower energy that's deposited in the first 5 radiation lengths. And they're statistically different. You can see that the photon has some probability to dump almost nothing. They can go more than one radiation length in. And then for the bulk, we get that structure where the shower max moves in. T max is the number of radiation lengths in, moves logarithmically. And if we're being careful, it's logarithmically with this linear correction, which is different for the electron than for the photon. Also, if you want to zoom in on the tail of this, it's not dropping with the radiation length scaling you might think it would. So different materials will end up looking different, even though we designed the radiation length scaling to prevent that. So there are long tails. And it's also, as it's traveling into the block, it's spreading out. The average opening angle when we scatter an electron isn't 0, it doesn't go right forward, it deflects. And the opening angle of our E plus E minus pairs from pair production are also non-zero. So these both tend to take the shower energy and move it laterally as well as deeper in. So we need to characterize our shower not just by its radiation length, but by the radius that contains some fraction of the energy. That's called the Moliere radius, which is this scale energy divided by the critical energy, and that scale energy is around 21 MeV times the radiation length. So as we develop the shower, this is the normalized energy per unit area as a function of the radius. And we start out at the bottom of this with a very sharply peaked energy deposition and a tail that's many orders of magnitude down. And then as we go through 3 radiation lengths, 5, 8, 12, 15, 20, this tail gets bigger and bigger, which is saying that it's getting smoother and smoother. So there's less difference between the peak and the tail as we go. We can calculate this E sub S. If you're wondering, I put a couple little tiny notes here. If you look at the slides later, that's an analytic number you get from Coulomb multiple scattering. All right, this is just showing the same thing, but now in fun 3D on linear scale. Here at the start of the shower, it's very sharply peaked, and then as we go out, it spreads out and dies out. The same thing on the log scale. If you are trying to get the right answer, you should not use these numbers. These are rounded out to make them easy to do kind of math with. There's a cheat sheet. X naught is about 180 grams per square centimeter. It's the total integrated depth that you have to pass through. And it's if you have a less dense material, the radiation length is longer in centimeters. Our critical energy is around 550 MeV divided by Z. And that's, again, rough. If you want the nice one, it's over here. The shower max just moves like the logarithm there. And then the dimensions of our shower. So if you want to say, how big does my calorimeter need to be transversely so that I don't lose the energy out the sides, or how deep does it need to be to capture a certain amount of energy? Got some rules of thumb here. Well, admittedly, this one's that's probably not the one I meant to leave here, but that's a little bit ad hoc. And if we do go to 2 mollier radii, we capture the vast majority of the shower. Okay. One more. A high energy muon comes in. It's got an energy above GeV. What happens? Nothing. I like it. Yeah, right through. It emits some soft Bremsstrahlung, but the Bremsstrahlung spectrum is pushed way down. We don't get, on average, the kind of hard Bremsstrahlung that would allow a shower to develop. And this is the beta block formula. I haven't given you the math for, but this is telling us about the deposition of energy in matter by different particles at different momenta. So we start with the muon, and then the same scale we can use for pions and protons because it depends on beta gamma, and that moves these scales with their mass. But this is where the electrons live, up at around 5 MeV per gram per square centimeter. And this muon at 1 GeV, muon 1 GeV, is living down a factor of 5 lower. We'll see a little bit of light, whether it's enough for our detectors to tell it apart from background, depends on the detector we built. Okay, so let's go back to my extremely fictional simplified experiment. In principle, I could have made this calorimeter out of ice, but not a good idea. So is it made out of lead? How do we get the signal out of this? What is the signal? It's light. Quick question, how transparent is lead to visible light? Not very. If we did this, these will heat up. They will absorb the energy and we will see nothing. So that's not a great plan. Yeah, and I already said this, because the Bremsstrahlung spectrum is pretty flat in terms of the power per unit energy, we have some high energy photons and a bunch of these low visible light photons. So we generally design our calorimeter to be transparent to something kind of near the visible spectrum. And now we have 2 options. We can make our calorimeter out of something that is dense enough to absorb the energy quickly and also transparent to some sort of light it emits. If you're really experienced in this, you'll know that me picking lead glass as a nice dense material that also happens to be transparent is not a great example. Does anyone know why lead glass is not a great example? All right, you can ask me later. Okay, so we can make it out of this dense glass that happens to be transparent, and then we put a photodetector somewhere on it, and we're done. Or we could make a sampling calorimeter where we have layers of lead and then pieces of something transparent that we can collect the light in that transparent block, route it out to a detector, and then do that repeatedly, sum all those energies together. So that's homogeneous on the one hand and sampling on the other. Homogeneous detector. Now, the trick here is that we have something that is dense and transparent to its own light. And again, I'm leaning on this example pretty hard because it's pretty common, like glass. And they show up in, for instance, the CMS calorimetry. And that is to make sure they don't lose any of the energy from the photons. So they can do Higgs to photon-photon. The advantage is you don't lose any of the energy. You're sensitive to the entire shower, and you have good linearity. If you double the energy, you double the response of the crystal. But you can't subdivide these crystals up forever, or you basically turn them back into a sampling calorimeter, and they're expensive. Other examples, there's other crystals that do this. Germanium is something you might have seen in an undergrad lab, but it would be a terrible thing to use here for a number of reasons. And if you're curious, you can ask me later. Let's go on to the sampling calorimeter. Here we have a hybrid detector made out of 2 different things. We interleave our absorber, which is what is the dense material that creates that Bremsstrahlung and paraproduction that makes the shower develop. But then we interleave something that has a much longer radiation length. It doesn't participate much in the shower, but it is transparent. Yeah, and X naught can be 10 times larger or even higher. The downside of this is the Harabi ecal, a shashlik. I don't know why this is the name we centered on, but it's a skewer, like a barbecue skewer. So it's you alternate two different kinds of things on it, and same deal here.
Are we hearing questions?
So it has some downsides. Because some of the light from the shower is lost in that absorber, if it's lead, then only the light that is produced right near the edge of it is going to make it into the scintillating part, the transparent part. So we're not going to measure all the energy, we're just going to measure some of it. And we're going to have to multiply that by whatever factor is our sampling factor. However, depending on exactly how the shower develops, we might lose more or less of it in those absorbing, but not in those absorbing layers. So if we move our shower max so it occurs right after that, you'll see more of the light than if it happens right before one of those layers. Also, because you're sampling from a smaller region, you have larger uncertainty. So Landau tails of the distribution of how many photons you might see make it a little bit noisier. In terms of practical concerns, it's cheaper to do this. In general, something like tungsten is expensive and something like plastic is cheap. And you have a lot more options of how to segment this because it naturally has light coming from different spatial regions that don't overlap because there's absorbers between it. The light coming from this first front blue layer has nothing to do with how many photons are coming from that absorber plate in the back. So we can actually get some spatial resolution that we can't from a single block crystal. Then the next challenge is how do we get the light into a signal that we like? And this is just a kind of sampler. You can put photodetectors on the end of your monolithic blocks if it's monolithic, or if you're scintillating in little regions, you can route that light through light guides to photodetectors. Photons, unfortunately, are incompressible. So if I want to get all the photons out of one of these, I have to have a cross-sectional area as I go to my light detector that never gets any smaller. So that's pretty spacious. There's a cute trick which is shown here. Yeah, the wavelength shifter. You can get around that incompressibility for a one-time cost. This is a plastic that's coated that absorbs the photons in one wavelength and re-emits them in the other. And I wish I had brought a sample here because if you just hold it in a room, the ends glow because light's going into it and then totally internally reflecting inside it and coming out in a different color. So you could do this to get around the major problem. Signals have to come out one way or another. So if you want all that light to come out without doing something to it, you need a lot of the solid angle of your detector devoted to getting that signal out. The more channels you have, the more you want to segment this, the more space you need for separate routing. And that breaks the hermeticity and the idea that you can capture all the energy in these crystals. This is another one that shows up a lot more lately, which is some block of tungsten or lead or something else into which we have managed to put scintillating fibers. So they don't have any depth dependent discrimination, but in exchange, they can have very good spatial discrimination, and we can hook up to photodetectors on the back, so the routing is a little bit less complicated. Or, of course, we could just put our photodetectors right in there with it, but they then form part of the dead area that we can't detect. All right. So we've talked about the mechanisms that generate the shower. We've talked about how we get the light out. How do these perform? In general, you'll see this written as sigma E over E. So our resolution on our uncertainty budget on the energy has something over root E added in quadrature with some constant term, added in quadrature with some linear term, 1 over E. And if you put these all together, you get something that as the energy goes up, the relative uncertainty divided by the energy goes down, which is very different than how tracking detectors work. Do I have that on the next slide? Yeah. So here is, as we increase the energy, here is our relative uncertainty, and it's dropping. The yellow, orangish dotted line here is our simulated prediction of how our towers perform in the S-Phoenix experiment. And then for different conditions, these are actual measured performance of what the energy is compared to what we know it is through some other mechanism. Schematically, tracking tends to do this. There's some combination of uncertainties that make it rise with momentum. So these are nice complementary things. If you had a really highly energetic particle in the tracker, it's going to be straight, and you're not going to have a good measure of its bending radius, which is what's proportional to its momentum. But in the calorimeter, you're going to have a nice precise measurement of it. And together, they can help you understand what's going on in the collision. These terms, the first one is something stochastic. These are intrinsic fluctuations, like the shower shape isn't deterministic. It's got all these quantum processes going on. Sometimes they'll develop a little bit early or a little bit late, and you can't get rid of that. You also have something about how you're sampling it, and there might be quantum effects if you have a photomultiplier tube, sorry, that has a quantum efficiency associated with it. So sometimes it sees one photon, does nothing. And then you have a linear term. These are deterministic, what I call deterministic non-uniformities. That is to say, they are literally, there's something wrong with the detector that's, in that one place, it doesn't respond as well as it should. So maybe this one crystal is a little bit smaller than its neighbors, dimensional variation. Maybe my readout isn't good at collecting light from the far corner. Or maybe there's energy leakage for showers that develop near the edge of one of these crystals. And then this C term is something like readout electronics noise. Maybe it's picking up the radio, or maybe there's some effect from previous events still lingering in. But in this general process, you'll see that for most calorimeters. All right. Questions about this kind of real crash course through calorimetry? I have to warn you, hadronic calorimeters are much messier, so it's going to get worse. I amended our earlier question. Earlier, I was doing DIS, so I just needed that electron. Now, for sake of argument, I have built my electromagnetic calorimeter out of sampling calorimeters there. But I want to do CITES. So I need to do something about the hadronic final state to see if it's got my charged pion in it. And we already did this. We know charged pions are not going to deposit enough energy in my calorimeter. So we're going to need something else to monitor them. There's a lot of symmetries, a lot of commonalities here. Like a photon, a hadron, even though it carries charge, or it could be neutral, but assuming it's charged, it still doesn't emit Bremsstrahlung. That's not enough to drive the shower development. So the photon does nothing until it has a substantial EM interaction, and then it starts depositing. Now that there's charged particles in this shower, they start depositing energy that we can measure. For the hadron, it is the nuclear interaction. So here's our hadron going straight through our lead. Oh. I like this slide. This is not my slide. If you want to see it in context, Brock Schmuckler's talk here last year, it's on the web. You can go look. But this is what's going to happen here. Our incoming hadron is going to lose a little bit of energy through ionization. That's not enough to start the shower. And then it's going to collide with the nucleus. And we're going to cause this spallation event. So spallation occurs in a few steps. As it's passing through, it will react with the dense medium, and it will produce some stuff. Some of it will be electromagnetic. And you see we also have some pions coming out and a neutron coming out. And then this incoming hadron continues on its way. Or it may no longer be the same identity, but the momentum is carried by something that's going straight forward still. It leaves, and then this nucleus has a problem because it's been heavily disrupted. Maybe it's been excited to an extremely exotic excited state. Maybe we knocked out some neutrons and now it's just something else that's unstable. So it's got some exciting future for it. One version, it can undergo fission, just break up into two objects that are then going to radiate neutrons, or it can just radiate and keep a core that is intact. Once we've done this, we have taken some energy and we've moved it into electromagnetic energy. So we're going to start to see an electromagnetic shower developing underneath this hadronic scattering stuff. So I took my detector that wasn't deep enough to see the hadronic shower, and I just stacked a bunch of them together. Nothing happens, nothing happens, nothing happens. Blam! I just destroyed a nucleus. I get some electromagnetic energy, develops a little shower there, and then some hadronic energy. And I've drawn them all as if they're traveling really highly energetically. Not all of the hadronic energy that shows up is going to be really energetic parts of this shower. Sometimes it'll be nuclear recoils that carry a substantial amount of energy because the nuclei are heavy, but don't radiate. So there's a risk of not seeing all the energy in the shower. But as we go, we develop the shower and eventually dump the energy into EM, or it goes out the back. The nuclear interaction length, kind of analogous to the radiation length, is this constant 35 grams centimeters squared times the cube root of the atomic number. It's basically the size of the nucleus. It's about 10 times larger, 10 to 20 times larger than the radiation length. So hadronic calorimeters need to be bigger. Our best hope is that after that spallation, we get some pi naughts, because they don't last very long and they'll decay to 2 energetic photons. And that drives the part of this shower we can see. So the hadronic calorimeter is just creating electromagnetic showers. Those are what we're seeing in it. And the question is, how much of this are we going to see? If we start with the pion, then we have a good chance to do something called charge exchange. So our charged pion can become a neutral pion, and now we're in luck because that will decay to 2 photons and produce a purely electromagnetic offspring. So if we started out and that first collision event transformed our pion from the actual particle collision we care about and turns it into 2 photons, now we just have an electromagnetic shower. Or any other version, if we started with a proton, it doesn't tend to make pi zeros due to baryon number conservation. So we make pi plus, pi minus pairs, but we don't make pi zeros. And that means that we have hadronic energy that continues to stay hadronic. This showing as a function of the pion energy, how much of the shower is electromagnetic. So we'd like this to get up towards 1, but it does not. So we're going to capture a energy-dependent fraction and also dominated by random events we can't control. And again, some of this energy is just going to stay hadronic the whole time. Nuclear binding energy that we spend through the spallation event, we have to break up that nucleus. We don't necessarily see that. It's just, it's lost. It's just the breakup energy. Neutrons that come from the evaporation phase of those daughter nuclei returning to stability, those neutrons may just leave the detector or they may thermalize. And nuclear recoils below the sensitivity. There's not producing enough. They don't have enough kinetic energy to have Bremsstrahlung radiation that we can detect. Nevertheless, these showers develop in rough analogy to how electromagnetic showers develop, just bigger and with more variation. So we have an interaction length just like before. We have a shower max that moves logarithmically into the detector with energy. We can talk about containment in terms of how much longitudinal detector do we need to capture 95% of the shower. And we can talk about something, the equivalent of the Moliere radius here, but it ends up just being the interaction length again. But it produces, the same rough shape. This is the number of nuclei. I thought that was energy when I put it on there. I'm going to think about that. My gut says that scales properly with energy, that we can still just talk about it in terms of the energy development of the shower. And for funsies, this is the ratio of the nuclear interaction length to the electromagnetic radiation length as a function of z, and it's just rising linearly. So for light particles, the two showers develop at about the same rate, but then you have to build a gigantic detector. And for for light nuclei, for heavy nuclei, we get a longer radiation length relative to longer interaction length relative to the radiation length. They both get shorter, but radiation length drops faster. Takeaway: hadronic showers are slower than electromagnetic. And then they're messy because of that lost fraction. So depending on how much energy we're depositing, we have a MIP, that minimum ionizing particle. It doesn't do anything in the detector. So whatever energy we do see is about the energy it did deposit. Or we could have our shower start with a pi naught, or not with a pi naught, start with a pion or produce a pion early on, in which case we get an electromagnetic-like shower, E, or it could not do that for a while, and it's dominated by hadronic daughters, and the amount of energy we see compared to the amount that's actually deposited, if we simulate this, is low and very broad. So we have a problem because we want to detect the energy of the particle. And depending on what happens in this quantum, random process, we're either going to get most of the energy or not much of the energy with a huge spread. We have a pion. It's the response to our detector to a pion of energy E is the response it would have to an electromagnetic component that's whatever electromagnetic fraction we have, plus the response to the hadronic component times 1 minus that. And we generally don't write that with the R sub E's, but so we'll write it as the pion response is the electron response times that fraction plus 1 minus the hadronic response. And if we try to form this ratio, what is the ratio of E over pi? We discover that it is just not linear. The response to an electron versus a hadron is roughly flat, or is roughly constant with energy, but the rest of this stuff changes with energy. So if we wanted to, on average, correct the energy that we observe back up to the true energy with some scale factors like we did for sampling calorimeters, it's just not going to be linear. It's also, this has got a huge spread. So large fluctuations mean that when you see that same error budget for hadronic calorimeters, you're going to see a much larger stochastic term. Okay, now what? So we talked about electromagnetic calorimeters. Did I? Oh, yeah. Unless we find a way to compensate for that nonlinear hadronic response. I'll leave that there. So now what? Well, finally, we're just going to put the real detector in here, and we're going to talk about the calorimeters that are in the EPIC detector. Some of these are actually under construction now, or building large prototypes. They take a long time to build, so there's a lot of repetition. Let's look in the backward direction. Sorry, you've seen this detector before? Yes? Okay. It's got the electron going direction, which is called the backward direction. And that's basically built to see the electrons. So it's pretty skimpy. Electrons have much less energy than the forward going hadron side, which is much beefier to make sure that it captures it. Why does this have to be much bigger?
Because it's hadron, right? Then direction. Cross section is less.
Yeah. It's got to, I can throw hadrons back this way. That can happen. But if they go that way, they're going to be less energetic. So the hadronic calorimeter back here doesn't need to have as many interaction lengths to fully capture it. The backward ecal, how many? Okay. Its job is to look for that low Q squared final state electron. So the trick is to make sure that it can tell an electron from a pion in the electromagnetic calorimeter and also use the hadronic calorimeter behind it to tell that apart. And it's made out of lead glass, which continues to not be a good example of a homogeneous detector. It's got 22 radiation lengths, so it can contain the entire electron shower, and as is traditional, it is divided into blocks. And I didn't write this down, but this is probably going to be on the order of the Moliere radius so that it contains the showers. You actually probably want it to be a little bit smaller than that because you don't want your shower to be in one tower. Once it's within one tower, you can't tell where spatially it is, where if it strikes multiple towers, you can average them to figure out where the center of the shower is. And there's our resolution, 2% over root E plus flat 3% stochastic term. I felt kind of obligated to show all these. It's a little bit repetitive, so I'm not going to go through all the details. You can come and read these slides if you want to see everything, but I'll pull out some highlights. So this is the barrel EMCal. It's made out of these sectors, and it is not divided into towers in the traditional sense. Instead, we have longitudinal fiber, transverse fibers in the context of calorimetry, because we talk about longitudinal being this direction as we're developing, and instead these are going lengthwise through it. So they have a wavelength switching fiber that goes through a long segment of this, and they read out the light that makes it to both ends. So you can use timing and amplitude there to figure out where along that shower deposited that energy. In addition, you can, I don't know how well you can see it from far away, you have these hybrid layers at the bottom of this where you've interleaved some active detectors that are actually watching the particles pass directly through them. It's not a great picture, but it's a pixel detector. And as the shower passes through it, we can watch every ionization event that occurs in this little detector. So you get a really high granularity picture of what the shower is doing at the front. Why would I put those there? Why did I not want to say, what is the shower doing at the back? If you're looking for inspiration, this detector is built for a certain task. So why did I put those at the front? I didn't do that. Why did they put them there? It's the right move. What are the two kinds of electromagnetic showers we talked about? Those are the calorimeters, homogeneous or sampling. This is a sampling one. I can tell because they interrupted the shower with something else. But we talked about photon. Oh, sorry, go ahead.
Right at the front, does that mean you're trying to get the electrons with them or electron positrons?
Yes, that is what we're doing. We're doing it for the opposite reason. It's because a photon is going to travel into this for a little ways before it produces the start of the shower. So if we can really pay attention to where that shower started, we can discriminate pretty well between whether it was started by an electron. Better, we can improve our ability to tell electrons and photons apart. And in particular, we can tell whether a photon that we're looking at is two nearby photons from a pi zero decay. When the pi zero decays, if the pi zero is carrying a lot of energy, its two photons are pretty close together. If they're pretty close together, I have to do some very subtle exploration of how the energy is deposited as we go deeper into this, because it's just going to say, instead of starting with, one E fold of the energy, it's going to be twice the amount of energy you'd expect because there's two photons in the initial state. But for DVCS, we really want to see single photons. So we want to be able to see if those two showers are one or two showers very, very close together. And that's another good reason to have this 500 by 500 micron pixels to look at the start of it. Mhm. The 4D MCAL, it has to deal with living in a world that's got a lot of highly energetic stuff going through it. And this design is similar to, inspired by the S-Phoenix design. And I think it's pretty neat. So I'm going to tell you a little bit about how it's done. This is what the detector looks like when it's done. These are a bunch of fibers, scintillating fibers that are embedded in a tungsten block. And how do you embed fibers in a tungsten block? In principle, I guess you could try to laser ablate tiny little holes. But what we actually do is we put the fibers in some holders here, and then we'll spread out these little blocks to the ends to keep these fibers straight. So we'll make that fiber matrix, and then we'll stuff it with little granules of tungsten. We'll just pack it in with tungsten dust and impregnate that with as much epoxy as we can and try to keep the density of it solid to make a thing that looks like a tungsten block, but is partially epoxy by weight. The challenge is to make that uniform, because that has to be done more or less by hand, and you can't tell by eye whether this is 1% or 3% or 7% epoxy. So that is an example of that deterministic inhomogeneity. So these different blocks are all going to have slightly different response, and that's going to mess up that's going to have a price in the resolution. Let's see, right? Yeah. So this one has a resolution of 5% over root E plus 1%. This one, 10% over root E plus 3%. The nice thing though is that we can put all the sensors on the back of these blocks. All right. The backward HCal. I looked really hard. I wanted to get you that resolution for sake of argument, but best I can tell, really no one cares. The backward HCal is not producing the main physics. We'll see. There'll be hadrons in it, but we want to mostly just make sure that we can tell what is and isn't an electron. That's the heart of its job, is to look for whether a shower continues past the end of the electromagnetic shower and the calorimeter. And now that I'm here, I'm going to stop listing them in terms of radiation length and start talking about interaction length. It's made up of bricks, which is this. I'm going to skip over to the forward one, which is the same sort of design, but just the smaller cousin of the forward hadronic calorimeter. Just making these tiles stacked on top of each other. And because they've got a budget, they have a custom readout chip. That one's job is to detect the forward-going hadrons. They're very energetic, so it's very deep, which is 6 interaction lengths instead of the previous 2 and change. And then the barrel sits between the two of them. And this did not. This is the S-Phoenix detector many years ago now, in 2021, when we started putting it together. Pretty soon it's going to look like this again as we take it apart. And it is going to selflessly donate the hadronic calorimeter barrel to the EIC. So you'll get the same sort of setup that we have. It's projective in the sense that these towers, these blocks, aren't all the same. They each point, and you can't see it, I apologize, but they all point towards where the primary vertex is, so that the showers develop longitudinally into them and don't cross a bunch of them. And then they do the opposite of what I just said. The powers, this is looking at it from the side. This is looking at a little segment of the radius. I'm going to draw that over here because it just did not scale. So if our interaction is here and our shower develops, or sorry, not shower, we have a jet, but we're going to have a highly energetic leading particle in the jet, and it's going to create a shower. What we don't want is to miss it because there's a seam between two adjacent tiles, and the material budget there, instead of being lead, is a little bit of plastic and some space because we couldn't get them to match up against each other. That'd be bad for us. So what we do here is we make it not projective in this direction. The tiles are all tilted a little bit, so there's no clear shot through them. And they're outside the magnet, so you can't even get around it by having, a perfectly curved hadron. There's no straight line through them. You must deposit energy in them. So it does mean that we don't have the same spatial resolution we get with a purely projective geometry, but it really improves the hermeticity, so our ability to capture the entire event. And they do the same trick that a lot of people do. They use wavelength shifting fibers to transform the light from whatever the scintillators are producing to something that can totally internally reflect, so that they can reduce and compress the cross-sectional area they need to get most of the light out. Okay, I want to say a little bit about stuff that may or may not show up at EPIC, but is neat ideas in the future. The reason for calorimetry is to measure the energy of hadrons, but often hadrons are not on their own. They're in some sort of jet. There's a lot of stuff coming out. And a idea called particle flow is that rather than treating the tracker and the calorimeter as separate beings and measuring the calorimeter energy and measuring the tracker momentum from all the charged particles and then doing some correction for the neutral ones we can't see there, we can just do really careful bookkeeping. We can match every particle in the jet to where it strikes the hadronic calorimeter and try to match it to the energy depositions so that we can identify which depositions come from neutral particles. And this means that we're not going to double count energies when we're trying to reconstruct the jet, and we'll get a more precise result. Yeah, I already said this. So by resolving the particles within these collimated jets, we can see if and how many neutral particles there are. Remember that high energy, the tracker doesn't give us a good measure of the momentum. It just gives us kind of straight lines. So we can't tell whether a really big shower is from one highly energetic hadron or energetic hadron and a neutral hadron going near it. But if we can resolve those two showers separately, then we can see them apart. And that can improve that stochastic term that is so gigantic for hadronic calorimeters. We could also do a dual readout where we measure not just the electromagnetic shower, but the Cherenkov light that's being produced in it. And that gives us two independent monitors that are not identical. So that we can get a better sense of the EH response per shower. And in principle, make it identically one for every shower, which would be the perfect compensation. And the last one that's pretty neat is the readout for these is generally not super fast, but if you make it fast enough, you can resolve the developing shower and learn a lot more about its structure. And you can also do time of flight like particle ID. So these things are not technologies we are ready to implement today, but they are things that people are thinking about. Okay, to try to sum up. There's two kinds of calorimeters. There's the electromagnetic calorimeter and the hadronic calorimeter. And they have some development. It's random, but in both cases, the structure of that, how the shower develops, is related to how it was started. Whether it was started with an electron versus a photon, whether it was started with a pion versus a proton. So there's some hints in there if we can get the information out. Hadronic showers are much messier. That spallation process means they're much larger, and the uncertainty about what fraction of it is being dumped into electromagnetic energy means that they are not as precise as electromagnetic calorimeters. Yeah, and so some of the energy will just be entirely lost to the reconfiguration of the nuclei within that material. In both cases, the energy that we measure is the electromagnetic energy. So even in the hadronic calorimeter, we're just measuring the energy that's dumped into photons through that electromagnetic shower. And we have kind of two choices of how to collect it. We can alternate layers of dense absorber with layers of efficient light transmitter, or we can make it homogeneous, one thing. These measurements are inherently destructive. If we built our calorimeter right, the particle does not survive. It comes to rest, it annihilates, or something. So that's, you better put the hadronic calorimeter at the end, because there's no information about the particle trajectories that survives past there unless it's a muon and just doesn't cause any energy there at all. But calorimeters have an important purpose. They measure that energy in exactly the place where the momentum that comes from a magnetic tracker is poor. So they're an essential part of any modern general purpose experiment. Thank you very much.
So wavelength shifting fibers, the attenuation isn't as great as like a clear optical fiber. What's like the benefit of the wavelength shifting? So is it more like sensor friendly?
It can be more sensor friendly, but the real win is photons are not compressible. Once I produce the photons in my scintillating layer, if I want them all to come out at their original wavelength, I have to make the cross-sectional area of my light pipe nothing less than the cross-sectional area of the side of my sensor. And that is a lot, taking all, but if I pay the one-time loss of converting, with some efficiency from the scintillation light into a different color, then I can compress. So I go from needing a very large cross-section to just needing one fiber. My collection efficiency on the fiber is perfect. The attenuation is worse, but I only need, a tiny fraction of the cross-sectional area.
Then I have another question. Sure. So this is, excuse my naivete, but so let's suppose something weird passes through the ecal that's not an electron or a pion. Could the ecal tell the difference?
In principle, the Bremsstrahlung spectrum has to do with the mass. So it is a really bad device to measure that. But it has, to misuse the term, it has some analyzing power to tell the difference. But in practical sense, there's going to be electronic noise in here in our electromagnetic calorimeter. So if a very small photon response shows up, we generally won't register it in any meaningful way. We do zero subtraction to compress our data. We don't record the things that we think are zeros. So we have to guess what zero is. And that's going to be a pedestal with some variation around it. We pick a spot on that. And if those fluctuations are small compared to that, we simply won't keep them. So we just won't see it. Welcome. Those are good questions. Yes.
So those three parameters for the resolution A, B, and C. You didn't quite show that third parameter here, yeah. Oh no. So when you give the actual reading in the SCAL and ECAL.
I was going to try to go back to the definition of it there. This one.
Yes, but in the slide number very large, 651, you only have the A and B. You have not.
Yeah.
See why.
That's what people are reporting right now, and I'm not sure why. If I had to take a guess, I would say that we're not yet at the point of building a large prototype where we can actually measure that noise term. So we're doing something idealized. We're not talking about the read electronics yet, but I'm not sure on that. Yeah.
Could you please go to slide 44?
Yes.
Yes, I'm just curious about the plot where you were showing the electromagnetic shower fraction as a function of pion energy.
Yeah.
So how do you calculate this fraction? You look at the shower profile from the calorimeter and then.
I don't know how they did this. Okay. And to be honest, it's NIM. So it's not enough of a clue. NIM can talk about expected performance of a detector, but it's also a place where you might report the performance of a detector. So I'm not actually sure if that is. I believe it's data, and that's based on the fact that it doesn't make great lines and there's error bars, but I don't know how they did that, to be honest.
Yeah, I want to ask about this picture.
Okay.
I feel
Oh, this picture.
Yeah, I feel for the opposite charge particle, it happened.
So the particles do deflect inside the magnet, but the magnet's there. So once they leave the magnet, you're right. In principle, if we have a charged particle that has the right sort of deflection, we can get pretty close to it if it happens to get through the magnet in that direction. Because they are straight lines. The ability to do that requires that it bend in the magnetic field, though. And for it to bend substantially in the magnetic field, it must be low energy. And if it's low energy, it will deposit more of its energy in this path, and it'll deflect more as the shower produces. So the only way to make a problem is to make this particle soft enough that it won't be a problem anyway. Does that make sense?
So what did you say that lead tungstate was not an ideal?
Because it's not producing Bremsstrahlung light. So the whole premise was that these calorimeters are based off of measuring that soft Bremsstrahlung spectrum. But what drives the photon yield in lead tungstate is Cherenkov light.
Right.
It's still proportional to the number of particles traveling through it, so it still has a nice linearity, but it's I completely tried to pass it over, except I did point out it to see if someone would ask. Yeah, it's Cherenkov light.
What is the best option? Yeah, better than the lead tungstate.
Oh no, lead tungstate's a great choice. You have the budget for it because it has that linear response. Anything else? If you had infinite money, you could just build a gigantic crystal calorimeter. Don't build a hadronic one, because that Cherenkov light will pick up hadronic Cherenkov light too if it's traveling fast enough. And you could have the whole thing active. You lose nothing. So yeah, if you have the money, but it's a money thing. So the best one is the best one you can afford.
We're ready for coffee, so let's thank. Half an hour. Thanks to them.
This one is also the heaviest one you can support in your carriage because lead tungstate, yeah,